Hello, Math 30-1 students. So today we're looking at lesson 9.1. I just want to show you this meme first. So a guy says he was questioned on a plane for doing math during a flight. So the woman thought he was like doing some crazy stuff, and he was writing in a foreign language and script and stuff she didn't understand. So she got really scared of it and then told the flight crew she had security concerns. And when he was questioned, he was just showing that it was differential equation, which is math. So we're going to be analyzing graphs, looking at the asymptotes, the points of discontinuity, which is something we did look at in our transformations unit. We're just revisiting it. So first things first, we have an equation. It's slightly different, so I want to show you this kind of special piece here, where if we factor the bottom, we can find the vertical asymptote. So I factored the bottom as x plus 4 and x minus 2, and I got x equals negative 4 and x equals 2 as the vertical asymptotes. And then you can graphically do the rest. So I'm going to graph this right now so I can show you what's actually occurring here. So I'm going to graph, in brackets, 3x divided by bracket x squared plus 2x minus 8. Close your brackets, graph this here. So remember we stated that there is a vertical asymptote at negative 4 and negative 2, and that's why the graph goes and approaches it but doesn't actually touch. You'll see that the graph goes to positive infinity on the right side of that negative 4, and on the left side it goes to negative infinity. And then for the asymptote at x equals 2, we know that the left side is going to negative infinity, the right side is going to positive infinity. So let's look at the intercepts. If I go trace, 0, enter, that's going to give me both my x and my y intercept because they are the same. So I'm going to write my x-intercept is equal to 0 and my y-intercept is equal to 0. Now, if we look at the end behavior, we're looking at that the graph, as x becomes very large, both if I'm going to the positive direction, will approach the y equals 0 line. So there is a horizontal asymptote, but only on the ends. If you guys look in the middle where my tracer is touching right now, there is no horizontal asymptote right there. It can actually go through it. So in the middle, the graph is going through this horizontal asymptote because if I only look at that piece of it, that piece is allowed to have x equals 0 and y equals 0. So in this graph, the asymptote where it gets really close to it but doesn't touch it only exists on the ends. When x is very big, meaning positive infinity, and as x approaches negative infinity. So only for those ends, it can't cross the asymptote, but in the middle, in this case, it does, and it is allowed to cross the asymptote because a portion of the graph, that asymptote doesn't affect it. Like it's going to approach it, but at that point, it can't go through it. So that's kind of like a little like anomaly. So it's a little different than what we've looked at. So the horizontal asymptote is only applying to the ends when the x's are very big, either positive or negative wise, but not to the middle piece, okay? So the domain here is that x such that x cannot equal negative 4 and 2, x here. So that's all they wanted us to focus on right now was the domain. So in calculus, you would then focus on the range, and they would you would actually have to look at it in pieces because not all of the graph can have y equal to 0. So we would actually have to kind of do piecewise functions for that, but that's more of calculus. So if you're going to calculus, you might see that later on. But we just want to answer what is the domain, which we did, what's the x and y intercepts done, and the equation of the vertical asymptotes. Good. So the sketch that we would create, I would have my dotted lines at negative 4. and at positive 2. And my graph is going to get really close to those lines, but not touch them, right? Versus in the middle, it actually does go through the 0, 0 value and then goes down, right? And then same thing here, it's going to approach those asymptotes but not touch them. Okay? So that's what I'm looking at. X and Y, label your numbers as well. So that's a recap with something a little bit of a different example, just to state that sometimes you can go through the horizontal asymptote because it's only applying to the end. So that's a special case. Let's review factoring. Okay, so factoring, you want to break this up. If there's a greatest common factor, you want to take that out first. So if you guys look, there's a 4 that's common for all of it. So I'm going to take that out by dividing, and I'm going to be left with x squared plus 8x plus 7 left inside the bracket. And then I'm going to look for two numbers that multiply to this and add up to this. So this is kind of like the fast technique for it. So 4 would factor as x plus 7 and x plus 1. So that would be factored for. The next one, when we have a number that can be factored out.
Hey staff, we're looking for a little bit of help on a video that we're creating. We need 8 or 10 teachers to gather with the appropriate social distancing in the front atrium near the main entrance by the office. If you're able to come down for a quick 2 minutes to shoot a part of our video, we'd appreciate it. Thank you.
Okay, so we're going to multiply the first and the last coefficients, the leading and the constant. Leading coefficient and constant, we're going to multiply them together, and we're going to have to find.
As well, if you have visited Tim Hortons or Starbucks today and you have a Go cup sitting on your desk, could you please bring that to the front as well? Thank you.
We're going to multiply them together, and we're going to get negative 24x squared. And we're going to have to add those two numbers, add the numbers together, and they're going to have to always equal the middle term, which is in this case 5x. So multiply the first and last, that's what we have to find that multiplies to it and adds the middle, okay? So in this case, the number that I found that works for both would be 8x and negative 3x. Okay, so if you multiply them, you get negative 24x squared, and if you add them, you get positive 5x. So a trick that I use to factor that I've shown students, and they seem to like it because it is a quick method. If you have another method that you remember that works, go for it. You do not have to use this method. But what I do is I write the leading coefficient twice with the variable. Okay, so leading coefficient with the variable twice. So I'm just writing this part, write it twice. And then I'm going to divide by these two numbers I just found. I'm going to divide it by 8x and negative 3x. And then all you have to do is simplify the fraction. So for example, 2 and 8 can simplify as 1 over 4, right? So I would write 1 over 4. X squared over x would just be x left at the top. So that would be simplified from your first fraction. Your second fraction, 2 and negative 3, can't be simplified any further, so I would leave those. But x squared and x can be simplified as just x, because x squared divided by x is just x alone at the top of the fraction. These are your factors. Your factors are x plus 4, okay, because it's a positive 4. And the one you don't have to write. And the other fraction, or the other factor, is 2x minus 3. So that would be factored form to break that up. The last one is difference of squares. So what I do is I write out two brackets, and I square root each part. So if I square root 9, I get 3 times 3, because 3 times 3 is 9. Square root of x squared is x, because x times x gives me x squared. And then you have to look at the entire negative 25. The square root of 25 is 5, so we're going to have 5 and 5. But to get a negative, we're going to have a positive and a negative in between. So that would be your factored form. So if you multiply those guys together, you would get back to 9x squared minus 25 once you simplify. Okay, so these are just some things that you want to remember, because for each of the following rational functions, we're going to have to factor first and then look at what we see. So the graphs of rational functions can have a variety of shapes. They can come from linear functions, they can come from quadratics. So we want to look at those non-permissible values. So that's going to give us those vertical asymptotes. We also want to look at x-intercepts. That's what's left at the top as factors. Those are x-intercepts. And we want to look at points of discontinuity, also called holes on the graph. Okay? These are where we create holes on the graph. They're these open, empty circles that the graph does not go through. They kind of stop there and then continue after it. So if you're not looking for them, you won't see them because they're really hard to find and you can't see them on the graph. You have to look for them from the equation form. So point of discontinuity, also called a hole in the graph, is a point described by an ordered pair. It has to be coordinates. You need to write it as an x and y coordinate. So don't just give me one of them, give me the coordinates of the hole. So it's where the graph is not continuous. There's this stop in the graph and then it continues afterwards, so there is a hole in the graph. So when you actually simplify and you see the same factors at the top and the bottom and you cross them off, so remember how we have like sometimes x over 2 and then we have x plus 3 and x plus 3 in rationals last year. Last year you simplified by crossing off the same factors. These crossing off items would give me a hole in the graph. So that's a single missing point on the graph that's represented by an open circle like that. Sometimes referred to as a hole in the graph. So we're going to have to pay attention to those. So this first example, if you guys look, this one doesn't have a hole because we don't cross off any factors that are the same at the top and bottom, but there are other things that we want to look at. So remember in the last lesson, when I did division, I was able to put it into that transformation kind of form. It's not really necessary because here I can look at the horizontal asymptote. If I just divide those two numbers, those leading coefficients together, 1 over 1, I know that 1 is my horizontal asymptote. So that's true if the degrees are the same on the top polynomial and the bottom polynomial. We also have a vertical asymptote when x equals -3 because I'm going to solve for x here. So that's my vertical asymptote. Okay, so VA vertical asymptote is when x equals -3. Horizontal asymptote is when y equals 1. X-intercept. This is where I can substitute y as 0 and solve for the other one. That's going to be equal to -2. So what I did was I said 0 equals x plus 2 over x plus 3. I brought this over, and anything times 0 will give me 0, so that would cross off the x plus 3, leaving me with x plus 2. Then I would move the -2 to the other side, and then that would give me x equals -2. Same thing for y-intercept, you're going to make x equal to 0 now. So this was for the x-intercept. For the y-intercept, you're going to make x equal to 0. So that's going to be 0 over 2 over 0 plus 3, which is 2 over 3. Domain. The domain x such that x cannot equal -3, so I'm using my vertical asymptote for that, XER. It can be anything else. The range, should be here, would be y such that y cannot equal 1 YER. This comes from your horizontal asymptote. And from here, I can draw a good kind of graph of what this looks like just from all those features that I just did. So first I'm going to outline those vertical asymptotes at -3, I have a dotted line. And at y equals 1. I also know that the graph is going through at x equals -2 and at the y-intercept of 2/3. Okay, so remember we're just staying close to that asymptote line, and I'm just going to go through those 2 points that I just plotted and then go downwards. Make sure you have arrows on either end. And then what I can do is I can use the graph to figure out where the other part is, but I know that the graph is actually going to be here. I can do a table of values if I really want to. So for example, 1, 2, 3, 4. Let's pick a point like -4. Let's plug it in. When x equals -4, what is our output going to be? So we're going to go -4 plus 2 over -4 plus 3. That's going to give me -2 over -1, which is 2. So I know that at -4, I'm going to have a value of 2. And then that's going to help me draw my graph because I'm just going to go through that value, staying close to that horizontal and vertical asymptote, and then put arrows on the ends. So that's my sketch. Label your x, your y, put your numbers down, all that stuff that I like. Actually, that should be, this should be 1, 2, 3, 4, 5, 6, 8, 9, 10, there you go. Okay, so label your graph correctly, continue labeling, and then just make sure all those features are included. Our next example, as you can see, we have a difference of squares at the top. We're going to factor it as x plus 4, x minus 4, over x minus 4. The reason we need to do that is because you'll see that it simplifies. This crosses off with that same exact factor at the top and bottom, and that's going to create a hole at x minus 4, which means that when x equals 4, we're going to have a hole. So what we're left with, what we're actually graphing that's remaining is x plus 4. This is linear with a hole. Okay, so we're going to have to find out the coordinates of the hole, which is called the point of discontinuity. So we need to find the point of discontinuity by substituting x equals 4 into the remaining equation. Okay, so we know that y equals 4 plus 4. Y equals 8. So we know that the coordinates, the point of discontinuity, is 4 and 8. So this is where we have to create a hole. So what I'm going to do is I'm going to go to my graph here, and I'm going to label 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Four and 8, I'm going to put a hole where a point should go, right there. And then I'm going to graph my linear function of x plus 4. And to do that, what is helpful always is to find the x and y intercepts, of course. So the x-intercept is make your y value 0, so we're going to have 0 equals x plus 4, because that's all that's remaining, right? So that means x equals -4 is a y-intercept, or is an x-intercept. So you're going to plot the x-intercept at -4. Plot a point right there. Y-intercept. Make x equal to 0. So we know that we have a y-intercept of 4. And now we're going to draw a line going through it as straight as possible. Use a ruler. Make sure you have arrows on both ends. And this is my new equation, okay? So what needs to be included? The key points are you need to write those points, you need to include the point of discontinuity, the x-intercept, the y-intercept, plot those, and then show what your new linear equation looks like, okay? So x plus 4, we have to have the whole to show that it used to be x squared minus 16 over x minus 4, okay? If we're doing the domain and range, I do want to show you how that looks like. We're going to have to use the coordinates of that whole to figure that out. X such that x cannot equal 4, the whole, XER. And for the range, we would have to say y such that y cannot equal 8 YER. So if you were to graph this, which I will, just to show you, so this would be true for any kind of whole. If you were to look at the table of values, that would give you a better kind of look of what you should expect. So if I'm graphing x squared minus 16 divided by x minus 4, I'm going to graph it. Now, as you can see, it looks linear, but looks can be deceiving because if I look at the table of values, I'm going to notice that if I scroll down to x equals 4, you can see that there's an error because there is no point there. But after that, it continues like normal. So we have to be careful that we look for these holes and include them in our descriptions. Otherwise, it's not fully correct. Our next example, example number 3, has x minus 4 over x squared minus 16. Again, we're going to factor it. So my advice to you is factor if possible. So what you'll notice is that you can cross off these same factors, and you're going to be left with y equaling 1 over x plus 4. So this is my new equation, or new function that I should be graphing. We do need to include the whole, so we're going to have x equals positive 4 will be the whole, but we need to find the y value of where that occurs. So when x equals 4, what happens to our y? We're going to have 1 over 4 plus 4, which is the same as 1 over 8. So our point of discontinuity is at 4 and 1 over 8. X-intercepts, let's see what happens. If we make y equal to 0, we would bring this to the other side to make it 0. 0 equals x minus 4. We would bring the 4 over, we would get x equals 4. But because this is where our whole is, that means we have none. We don't have an x-intercept. There are no x-intercepts because that is where the whole is actually going to occur. So they're saying that approximately where x was equal to 4, we would have that whole, but it's not going to exist. Another thing we should notice is that there's a vertical asymptote . The vertical asymptote is going to be when x equals negative 4.
Mr. Mahoney, please call 6406. Ms. Mahoney, 6406.
There's also a horizontal asymptote at y equals 0. Okay, so remember how we said that when the degree at the bottom is greater than the degree at the top, we're going to have a horizontal asymptote at y equals 0. So that was from the previous lesson. And then the domain and range is going to be x is not allowed to be, we're not allowed to have x equal to -4 from our vertical asymptote and 4 from our whole, our point of discontinuity. So x is an element of real numbers. Range. Range, y such that y cannot equal, should have that x such that and y such that. Y cannot equal our horizontal asymptote of 0 and our y coordinate of our point of discontinuity is -1/8. Actually, it should be +1/8. 1/8, +1/8. Fix that a little bit, there you go. And that's YER. Okay, so what you need to include are those horizontal vertical asymptotes and the x and y coordinate of your point of discontinuity. From there, we are going to graph this. So we're going to have to draw that vertical asymptote.
All right, good morning, staff. Just before you head off to lunchtime, as part of Sunday, Friday, we are going to have a bit of a scavenger hunt. The way this is going to work is we're going to announce an item. And when we announce the item, if you can find it, you must bring it to the main office. The first person to arrive to the main office with the item will receive a prize. There are 6
We got
rounds.
time for a
And
scavenger
in
hunt.
each round, the item
Okay.
gets more complicated.
So guys, we're going to draw our vertical asymptote and our horizontal asymptote at y equals 0. That's those dotted lines.
Friday, Monday, scavenger hunt.
Okay, so I've labeled my x and y coordinates. We have a vertical asymptote at -4, done. We have our horizontal asymptote at 0, done. We have our x-intercepts labeled.
All right, ladies and gentlemen, the first staff member to arrive in the main office with an active Inspire Smartboard pen.
So let's find our y-intercept
Good
as
luck.
well.
And if you're racing through the hallway, please maintain appropriate social distancing.
Okay, y-intercept -4 over, oh my gosh guys, -16 is equal to, if you divide the top and the bottom by 4, actually by -4, that's going to give you 1/4, which is 0.25. So we know that we should have a point at 0 and 0.25. So I'm going to draw a point right there, y-intercept. Remember, there's no x-intercept because we actually have a horizontal asymptote there, which means we can't have an x-intercept. So that actually makes sense. We also want to show that whole. So at 4 and 1/8,
Congratulations to Stacy. She has won the first prize.
we want
in the Friday Monday
to
Scavenger
draw
Hunt.
that, staying
Next
close to the
up, the
asymptote, going
first
as
staff
high as
member
we
to
can.
bring this item to the office will win a prize. A pink paperclip.
Okay, so we have one side of it. To get the other side, remember you can always do a table of values. You can always plug it in to see what you get. So, for example, I can plug in -5, x equals -5, and see what the y coordinate is, and then plot it, and that will give me a helpful hint on where I should be graphing my other part of the graph. So 1/.
That was a fast
Negative
one as
5
Alex DeRoche ran from her office across the hall. Our next item that will win you a cool prize is a protractor. Good luck.
Okay, so here we are going to draw the other part because of the point -5 and -1. Include that. Again, do you see how my hole is clearly shown with an open circle? That is clearly important, and my ends have arrows on them, so that is a perfect drawing, if I may say so myself. So no x-intercepts, the y-intercept 0.25. Example number 4, again, factor the top. X plus 3 multiplied by x minus 1. At the bottom, we have x minus 1. These two factors cross each other off, which means that we are going to have a whole.
Congratulations to Natalie Moore for winning that one. Our next item is a purple whiteboard marker.
A whole at x equals 1. So let's find the y coordinate. We can substitute for f of x. It says f of x equals x plus 3, which means that 1 plus 3 equals 4. So we have a point of discontinuity. At 1, 4. Let's look at x and y intercepts. So x intercepts, we have.
Congratulations to Andrea. We've got 2 more items to go in our scavenger hunt. The next one, tweezers. Good luck.
Okay, so we have 0 equals x plus 3. We're going to move that 3 to the other side. Negative 3 equals x. So that is our x-intercept. Our y-intercept, make x equal to 0, so it's going to be 0 plus 3, which means that 3 is our y-intercept. Plot those. So here we have our graph, our y, our x.
Congratulations to Megan Keogh. And now for the final item in the Friday Funday scavenger hunt, you must bring us a colleague's left shoe. A colleague's left shoe. Good luck.
Okay, our x equals negative 3, so we're going to plot negative 3, a point there for our x-intercept. Our y equals 3. There you go. What we're left with, remember, is going to be a linear equation. So this is going to be linear, but with a hole at 1, 4. So we're going to have to put 1, 4.
And congratulations to Amy Landry, who ran in the office and practically threw a shoe at us. So congratulations. That was the Funday Friday scavenger hunt. We'll be back later with Name That Tune 2000 edition. Have a great lunch, everyone.
Okay, so here we have a linear function. Try to make it straight. I would use a ruler. My ruler is just not working on, doesn't work on Promethean board. So I always find it messes up the drawing. So I just try to draw as straight as possible, but it should look linear. I'm actually gonna fix that because I'm really not happy with that thing. That's as good as it's gonna get. Okay, so make sure that your point of discontinuity is clear with that open circle. Analyze the behavior. We're still going to do the domain and range. So domain x such that x cannot equal 4. Now, since there's no vertical or horizontal asymptotes here, we only have that hole, the point of discontinuity, to not include in our range and domain. So y cannot equal 8, y-er. Good stuff. Example number 3. Oh, actually, before we get to that, we'll just kind of review. So remember x-intercept. You should be looking for the x and y-intercept. So these are kind of characteristics we want to look at with a rational function that helps us graph it. So remember, you can make y equal to 0. This is the algebraic approach. Or you can go in your graphing calculator and go second trace, I think it's number 2, which is 0, right? And then your y-intercept, you can make x equal to 0. And then you can go trace x equals 0 in your calculator and press enter. So that would be the algebraic versus your graphical approach. Your vertical asymptote, so when you have it in the form of a over x minus h plus k, remember our h is our vertical asymptote and our k is our horizontal asymptote. So that's one kind of procedure. Another procedure that you can use is if it is a fraction with the same degree, so if it's a fraction with the same degree, like 2x over x plus 5, remember we can divide by the leading coefficients to find our horizontal asymptote. That would be another procedure, right? Another name for vertical asymptotes is NPV. So if you find your non-permissible values, those are your vertical asymptotes, right? Point of discontinuity. This is where you cross off a factor. So when you cross off a factor from the top and bottom of your fraction. What's important is it has to be coordinates. Make sure that they are always coordinates, okay, x and y's. Your non-permissible value, what makes your denominator equal to 0? What makes your denominator equal to 0? Your range, remember, we're always going to have to say y cannot equal our whole value, our y coordinate. We're going to have to include that vertical asymptote, and then say YER, right? Actually, it should be your horizontal asymptote. And then for x cannot equal, here it would be your x coordinate, which is your whole, from your whole, and here your vertical asymptote, and then you'd say XER. Okay, so this one is for you guys to practice. So this one would be where you pause the video and try these two on your own. And then you want to graph both of them. You can graph them on the same grid, or you can graph them on a separate grid if you really feel like it. So it's up to you. So I'm going to do the answer key for this, but you should pause the video right now. Try this yourself. Okay, see if you understand and are able to do these questions on your own. So for this one, I would factor it, of course, for the answer. That would give us a non-permissible value when x equals -3. We know that the feature of the non-permissible value is that it creates a vertical asymptote. The behavior near the non-permissible values is the left end. The y is going to go to -infinity. The right end, the y is going to go to +infinity. And what that's going to look like is it's going to have two parts to it. So in this case, we're going to have that asymptote, that vertical asymptote at -3. 1, 2, 3. With the graph, if you were to plug in values of x at the top and at the bottom, you'd get 0, 0. So the x and y intercepts would be 0. So you are going to get something that looks like this. Now, there's a horizontal asymptote on that one, guys, at actually there isn't one. So whenever in that first case, there's no horizontal asymptote. The reason being is in this case, whenever you have the same degree at the higher degree at the top than at the bottom, you're going to have no horizontal asymptote. So I don't have to include that. Let's look at the bottom piece. The bottom piece, there was a point at -6 and -9. -6 and -9. And it kind of does the same thing. It just goes like that and then goes downwards. It goes to the left and then downwards. Okay, so that's what the graph looks like if you were to graph this on your graphing calculator. So I used my graphing calculator and I looked at the table of values and I just plotted a few of these kind of main points. Now let's look at the next one. The next one I would have to factor it and be left with x plus 3 and at the bottom 2 and an x plus 3. That means that there's going to be a point of discontinuity that is created. So x equals -3 was a non-permissible value, but that is creating a point of discontinuity instead of a vertical asymptote because it gets crossed off. Point of discontinuity. So we know that there's a point at -3, and if we substitute it into the x over 2, we're going to get -3 over 2 left over. So we should have a hole at -3 and -3 over 2, which is -1.5. So there's a hole there. We're left with x over 2. So that would be like the y-intercept is equal to 0, and the x-intercept, same idea. And all you want to do is now just connect them and create a straight line going through these points. So it's a linear equation with the slope being 1/2. Now, as x goes to -3, which is that hole, we know that the y value is approaching -1.5. Okay, and that came from this value right there. The left end of the graph, remember the y is approaching negative infinity because it's going downwards. On the right end of the graph, the y is approaching positive infinity because it's going upwards. Okay, so that's what I was looking for. Again, label your graph x, y, put your numbers down. Etc. Same thing at the top. You guys can continue that. Example number 6, they just want you to match and figure out what would be the appropriate graph that matches the equation. Try to not use your graphing calculator. Okay, so what I would do is I would factor this and see if there's holes or what kind of features are left over and see if you can graph it from there. Okay. So I'm going to do this one, but I want you guys to pause the video, try this one yourself, and then come back and check your answer. Okay. So for the first one, I'm going to factor it. I'll do it up here. X squared plus 2 at the bottom, we're left with x minus 2, x plus 1. So it doesn't help me cross anything off, but at least I know that there are 2 vertical asymptotes, one at +2 and the other one at -1. The only one that matches is this. So this one has to be the k of x graph because it has 2 vertical asymptotes. Okay? And we have this x squared plus 2 function, which is like a quadratic there. So that's going to be this bottom piece that we look at right there, quadratic. This one, x minus 1, we factor the difference of squares as x minus 1, x plus 1. So this one creates a hole, and you're left with 1 over x plus 1. So the hole is going to occur at +1. So that looks like this right there. So this one has to be your L of x graph. And finally, of course, we only have one graph left, but it's nice to see why. We're going to factor this as x minus 3, x minus 2 over negative x minus 3, okay? What I did was I reordered this bottom piece as negative x plus 3. And I saw that I had something similar at the top, so I factored out the negative. So if you factor out the negative, this is a way of helping you cross off terms that might have the exact same values but the opposite signs. So once I factor out the negative, I am able to cross this off, leaving me with negative x minus 2. So that's a downward facing linear equation with a hole at x equals 3. So there's that hole at x equals 3. This one has to be the M of x graph. Example number 7. So these are the interesting ones where you have to create the equations from looking at the graph. So things that are important are x-intercepts. You need to figure out what the factors of the x-intercepts are. You need to look at holes. You need to look at vertical asymptotes. All those things are important, okay? So we're always going to have this A because we don't know what that stretch is going to be. We have to assume that there could be a stretch, so we always put this A in front of our factors. And then we'll always solve for A by using a point on our grid to substitute, okay? So things that we see so far in this example are that we have an x-intercept of x-intercept equal to -1, which as a factor would look like x plus 1. Okay, so the x-intercept would always go at the top of the fraction. Okay, so the top would have our A and our x-intercepts. Any vertical asymptotes will go to the bottom of your fraction. So let's look at our vertical asymptotes. X equals, we have one at +2, and we have another one at -4. As a factor, we need to write it as x minus 2 and x plus 4. So the opposite sign that you actually get. The last thing we need to do is we need to solve for the A value, which is a possible stretch that could make our graph look like this, okay? So we need to insert a point that is given. Okay, so for example, do you guys see how there is a point at -5 and -1? So I always like to use points other than your x-intercept and your vertical asymptotes. Like don't use any of those points that you have already used to create these factors, because that will actually make zeros go in and that will cancel everything out. So I want to use a point other than your x-intercept or holes or whatever you have, and substitute it in this case. In this case, I'm going to use the point of -5 and -1. We're going to plug it into the equation to solve for A. So our y value is -1, our x -5, and we're going to solve for A. So -1 equals A. We're going to work with bedmass, meaning brackets first. -5 plus 1 is -4. Over -5 minus 2 is -7 at the bottom. Actually, yeah, -7. And we have -5 plus 4 is -1. So that's going to give us -1 is equal to -4a over -7 times -1 is +7. We're going to bring that 7 to the other side by multiplying, and that gives me -7 equals -4a. And lastly, we're going to divide the -4 to both sides, which means that a is going to equal 7 over 4. Okay? So our answer for this, meaning the rational function that represents the drawing that I have, would look like this. Y equals 7 at the top, the 4 would go at the bottom in your denominator, and then you would have your x-intercept value, your x-intercept factor, your x plus 4, and x minus 2 as your vertical asymptotes. Now, if you were to graph this, it would look like the picture that we have given. So that's how you check. Graph it to see if it looks the same. Next example. What's important here is we have a hole and we have an x-intercept and a vertical asymptote. So we still have to write that a value. Then we write our x-intercepts. Our x-intercept is going to be that x equals 0, which means that if you try to bring over the 0, you're just going to get a factor of x. So this is your x-intercept that I'm showing by writing just the x. We also have a hole at x equals -3. Okay, so when x equals -3, we have a hole When you make it a factor, it's gonna be x plus 3. Now, to create a hole or a point of discontinuity, you always have to have the same factor at the top and bottom. So we're gonna have to put an x plus 3 at the bottom as well, because by crossing those off, that's how we get that hole. So we need to include it in the equation. We also need to include that vertical asymptote. And in this case, the vertical asymptote is occurring at -2. So the factor that represents that would be x plus 2. Okay, that's x equals -2, vertical asymptote, which is x plus 2 as a factor. Lastly, solve for a. Okay, so we can use the point of discontinuity to actually plug it in for our x and y if we have no other points, because that will actually help us figure out our a value. So our point of discontinuity that they're giving us was -3 and 3. So let's plug that in because the stretch would still be the same and you'd still get this final image from it as well. So y was equal to 3. -3 would go into your x. Okay, so you would not want to include it in the, when you're doing this part, you would not want to include it into the cross-off factors for your hole because that would just make the whole bottom 0. So what I want to do is only include that point of discontinuity in there, and that will help me find my stretch, okay? So I'm going to put in -3 plus 2 here, and then solve for a. So I have 3 equals -3a over the bottom, which is -1. Bring that -1 to the other side, that gives me -3 equals -3a. Divide by -3 on both sides, a is equal to +1, which means that there is no vertical stretch. It's just the original graph, which is good. So here, in this case, the function that represents that would be y equals 1, we don't have to write, but we're going to write x bracket x plus 3 over x plus 2, x plus 3, okay? So even though there was no stretch value of a, we don't know that until we actually plug in a value. And in our case, we plugged in the point of discontinuity into it without the x plus 3's, because those cross off anyway, so you don't want to include that part, because you don't want the bottom and the top equaling 0. So that's the goal. You need to find out the a without making the bottom or top 0. So this is our function that represents it. You could graph it to check if it and see if it looks the same. Let's look at this right here. So what I want to do is I want to find out what this linear equation is. This is linear, so let's find out what that is. A linear equation, we can always write it as y equals mx plus b. This is our y-intercept, this is our slope. Okay. So in our case, we have y equals x, because our slope is 1 up, 1 to the right. Okay. For every point, it's 1 over 1, which is 1 over 1x. So 1x, you don't have to write. And then your y-intercept is 1, 2, 3. Your y-intercept is plus 3. So once you have that, that is going to go in brackets. Okay, so that is representing what would be left if we got rid of our points of discontinuity. But we still need to include those, right? So when we write our equation, we're going to have to write a we're going to have x plus 3, which is our linear equation. We're going to have to include our points of discontinuity. We know that one point represents 1, 2, 3, 4, -4, and the other one's occurring at 1, 2, 3, 4, 5, 6, right? So we have to have an x plus 4 to represent the x minus 4. We have to have it at the top and bottom because those need to cross off if it's a point of discontinuity. And we have to have x minus 6 at the top and bottom to show that those would also cross off, okay? Now, if we were to plug in a point, okay, now a point could have been the 0, 3, the y-intercept. If we were to plug that in, you would see that the a value would be 1, okay? Because we already got the linear equation, so we know that that is gonna match what's left over, so the A value has to be 1. But if you're not sure, you can always try it out and plug in that point of 0.3 into it, and you'll see that it does equal 1. So you don't have to include that A value. Okay. Our next graph, we need to figure out how would we graph this and get this. What is this? Well, without those little circles in there, the points of discontinuity, that represents the line of y equals 7. Well, that's a constant. So that needs to be part of your rational function, okay? So we need to include that. What we're missing, though, is we still have to do those points of discontinuity. We have one at -2 and another one at -6. So that means with this 7 constant, we're going to have an x plus 2 as a factor at the top and bottom. And we're going to have an x plus 6 at the top and bottom, because those are the things that cross off to create those holes. And then once they cross off, you see how we'd be left with y equals 7 as a constant straight line. Okay? So there's arrows on both sides, because it does continue on forever, all of these guys. Okay, so the investigation that's coming up, the investigation function from your notes, I'll post that. That will be what you're going to use to practice and submit to me. So we'll talk about that later as practice. Okay, so you want to complete your day's homework, and then I'll give you the assigned kind of homework or assessment afterwards to check that you're doing this properly.